And this year we had the EFRIP related meetings. We had the RIA user organization, which had to reconstitute itself into an EFRIP user organization. So that was a meeting which was hosted by Argonne National Laboratory in May. And at the University of Michigan, there was also a workshop which was EFRIP stimulated on atomic physics with rare isotope beams, okay, fundamental symmetry studies and so on, high sensitivity experiments. So that was there are issues which are now starting to really creating a better justification of the science opportunities and working groups, so that people start getting serious about it, because if you want to build equipment, you have to design it, you have to build it, you have to attract the funding, so all this takes some time. And at this meeting, I will get into this a little bit later. I'll tell you a little bit about the things which are emerging. Okay, so we're very seriously thinking about upgrading our cryo plant. Actually, I'm going to buy a new one to advance the science with a reaccelerator, become independent operationally from all the other instruments which we have to keep cool. I think already at the meeting at Argonne, the need and the opportunities for the energy upgrade from RIA 3 to a high energy. I mean, the EFRIP proposal said we're going to go to 12 MeV per nucleon uranium reaccelerated beam capability. But certainly going above the Coulomb barrier is a big step, okay, there. And that is something which we need to ponder about. We need to ponder about that if you upgrade the accelerator, you need a new high bay for the equipment. Actually, there's another reason we need space to assemble equipment for EFRIP. And also, as we have one office wing up, the proposal says for another one, and then the question is, when do we want to do this? Do we want to wait for 5 years? Or, well, probably not. You want to get going right away, so that we're not going into a space crunch. So all these things that need to be vetted, and there's now several players in play which need to talk about this. And then my favorite unfunded mandate is, there's no way we could have this user meeting over at the laboratory. We have a dinky little seminar room, which we can put some 60, 70 people in, and they feel somewhat uncomfortable with the heat. But we clearly, if we want to have a world-class facility, we need additional meeting spaces and a bigger lecture hall and all that stuff. And that is actually not called out in the EFRIP proposal, so this is what I consider another unfunded mandate. First time I brought this up, I was thrown out of the office, but I'll repeat this every time. After a while, people recognize, well, it's a real need. Okay, it is a real need, so we'll get there, and you can help us getting there. Now, let me talk a little bit about the EFRIP funding opportunity specification. So this is basically the extract. What is the scope, the technical scope of the facility? The Department of Energy called out when it launched the competition for the EFRIP facility. So we're talking about a 500 MeV per nucleon, 400 kilowatt superconducting heavy ion driver. Okay, so that is a blowtorch of an accelerator for the fragment for the primary beams. The initial capability should include fragmentation of fast heavy ion beams. So this is the stuff we've been doing at the NSCL in the past, combined with gas stopping, and that they're significant gains. So this will be significant R&D and reacceleration. So basically, research with fast beams, in-flight production, immediate use for experiments, stopping in a gas cell, extracting the beams for experiments at rest, like ion traps, or atomic traps or laser traps, and then also reaccelerating the beams for precision properties for experiments near the Coulomb barrier, below and above the Coulomb barrier. So basically it calls out all these ancillary equipments. Everybody knows that you need to do them. I won't bore you with this. Another thing which is important is it also said it should be capable of world-class scientific research program on startup, okay, which means we interpret this, you better have the user community ready to run the experiments, and when the accelerator produces rare isotopes, we want to have equipment which is tested and ready to go on day one. So there are a certain number of implications, and it also calls out to accommodate 100 users at any time at the facility, and that I will take to the bank and say, okay, we really got to get the second office building up sooner rather than later, because it makes a lot of sense to have the user community, you guys, coming in early rather than late. Okay, so, and of course we need to find a place so that everybody can work in a fruitful way together. Now the other thing is the sort of project delays. I mean, it needs to be designed, built, and commissioned for a total project cost of $550 million in 10-year dollars. In other words, these $550 million include inflation. Okay, so that makes the planning a little bit more juicy. It's in today's dollars, it is significantly less than $550 million. And then there's some other guidance which I don't want to go into detail, but I want to have them on record. Those may or may not change depending on how the project evolves. So this is, I think, not necessarily cast in iron in all its detail. Now, the science of EFRIP has been endorsed many times. You all are aware of this. Okay, we had several long-range plans. We had RIA, and then we had another long-range plan which endorsed EFRIP by ANZAC. We had the National Research Council do a study where it studied the science case for RIA, or what they call it, or what we called in those days RIA Light, a lower cost version. And the science case was strongly made. And so it's clear that we had sort of four fundamental pillars on which EFRIP is resting in its scientific mission. The first one I would call the properties of nuclei. So that's the classic domain of our nuclear physics. Okay, the classical many-body quantum problem. And I think what's important is the intellectual overlap to mesoscopic science, the science of many body systems, but where many is sort of counted in the number of hundreds to thousands rather than billions, okay, like condensed matter physics. So it has its own interesting aspects of it. The other very important science branch is the nuclear processes in the universe. To a large extent, this is the RP process and the R process, okay, explosive nuclear synthesis. This is where EFRIP will make a major mark. But there are also opportunities to study the equation of state of neutron-rich nuclear matter. That's also the properties of neutron stars, which EFRIP can have a real impact. Third leg is the test of fundamental symmetries. That is, of course, a field where you're talking about long beam times, high intensities. There are other facilities which will have a significant lead ahead of EFRIP. And we'll have to sort of see which ones are at the right time. But that's certainly, there's significant opportunities for EFRIP to have an impact on, for example, precision tests of the standard model. And last but not least, societal interactions, applications. And there, this is sort of the, what I call sometimes the opportunistic aspects of research. You got to have the right people come up with the right ideas. There are lots of opportunities, but those opportunities can only be realized when you have a strong applied community which is approaching the project with concrete plans. And since there's no funding for this, this community will also have to create the appropriate proposals to get the infrastructure funded for. It's beyond the scope of EFRIP, but there's certainly plenty of opportunities.